Yeah, hello and welcome to our lecture series on climate protection. As you know, this lecture series is a kind of method for science communication in the field of climate protection, and the IPCC reports as well as all scientific literature on research and solutions on mitigation of greenhouse gas emissions should also be presented in an easy and understandable way. Moreover, graphs and color maps should be readable for people with problems with color perception, you know, this red-green color blindness and so on. For this reason, I invited two specialists in this field, Achim Zeileis and Reto Stauffer. This lecture will help you also for your own scientific work to present your results in the best way. So Achim Zeileis works at the Department of Statistics at University of Innsbruck since 2010. And before he worked for TU Vienna, University of Dortmund and LMU Munich. Achim is author of numerous statistical software packages. Some of them might also be useful for your scientific work. In his research, he combines ideas from statistics, econometrics, and machine learning. Yeah, and Reto Stauffer is also working at the Department of Statistics and half-time for the Digital Science Center. I don't know if you are familiar with DISC. The DISC brings together researchers and teachers from various disciplines. It aims for integration and promotion of digitalization of scientific research. Reto is specialized in statistics and wrote a Python toolbox for colors and palettes, and maybe also this might be useful for you. So looking forward to their presentation, selecting and assessing color maps for spatio-temporal visualization. Welcome.
Yeah, thank you very much for the warm introduction. Nice to be here. It's also nice to see a few familiar faces in the audience. That's lovely. And also welcome to everyone online and who are watching the video later on. I have been introduced already. Maybe one hint or one additional note is by training, I'm actually an atmospheric scientist, and that is also when Achim and I got in contact in my early PhD career. And what we're talking today is something ongoing for multiple years and was actually one of my first papers, my scientific papers, together with Achim in my PhD back in the old days.
Like this? Yes. Thank you very much, Rainer Ingo, for putting this together. Thank you for joining. Also, welcome to those watching online. Very happy to be here. And yeah, as Rainer already said in his introduction, the talk is not about climate protection per se, but about something that is relevant if you want to communicate about climate protection, especially if you want to communicate scientific results and do it in a way so that you represent the information in a way that is easy to understand for everybody. And color is typically a prominent tool when doing so. And here I've included on the title page the warming stripes for Innsbruck. And I'm sure all of you know the warming stripes visualization, which is a nice and very recognizable way to bring out or to bring attention to this topic. And in terms of really communicating the exact underlying data, it's not the most suitable way to do this, though. So if we look at this, we see the different colors. Blue is for colder than on average, and then the lot of red at the very end is for higher than on average. But if we go to the web page of, let me see where the browser sits here. If we go to the web page, then the Show Your Stripes project has the warming stripes as the first visualization, but they also have these bar plots also with an axis on the left-hand side. And if you really want to transport information that people can judge how large or small the deviations from the average are, then this display is actually much better than the one with color. You can add color to it. Maybe helps to bring the point across, but for really judging how big is the deviation, something where we have length or points at along a certain axis usually works better. So to come back to this, so colors and data visualization are everywhere. They're ubiquitous. They're not always easy to choose, but they are something that is perceived as very suggestive, maybe even as fun, something that draws attention to a plot. And then we have to think about how can we choose these colors in such a way that they actually help to understand the point I want to make. That the underlying quantitative or qualitative information I've put in a certain data visualization, that I can decode this well. And sometimes, like in the show your stripes bar plot that I just showed you, the color is an added feature that I don't need if I use the bar plot representation. But sometimes everything really hinges on the data. We will see a couple of examples for this. What we have to keep in mind as a challenge in this is that about 8% of the male population will not have full color vision. There are typically various types of red-green color blindness. There are also other types of color vision deficiencies, but red-green deficiencies are the most common form. And they affect males much more than females. But 8% is clearly relevant, especially if you think about warning maps and things like that, that really everybody ideally should understand. And you have to pay attention that certain red-green contrasts might not be visible or distinguishable for everybody. And there might be other physical or technical limitations. When we started the presentation, we talked about that this display we have here in the room shows the colors really much brighter than the laptop I have in front of me, and possibly your laptops, or for those people watching from home. So the colors, the absolute value of the colors might be rather different depending on the technical setting. And we will to give you a feeling for this being not so easy. We have now a little game coming up, and there's a maybe to also tell you that things are not so easy, but they are also not quite as bad as it may seem after we have done the game. For choosing colors in the visualizations, we can deal with this. But I pass over to Reto to have a look what we will do with you now.
Yeah, so as Achim just said, how good are we actually at detecting specific colors? Is it important that a certain blue is a certain blue, or can we like identify a specific blue? And for that, as Achim already introduced, we would like to play a little game with you, like an interactive session. You can scan the QR code you can see on the screen. There's also a link. If you enter the link manually, you can use the /? C equal. That's a code for our common challenge. So you are competing against your colleagues, your participants in the room. If you don't use the code, you will be asked for a code. So that will be the code to enter our common challenge. So we also have a leaderboard at the end. When I find the browser, thank you. Yeah. So if you follow the QR code or the link, you will end up on this page where you can enter your name. In this case, Achim is entering his name, and then you can start playing. And what the game is about, it will show you a specific color for a few seconds, and then you have to select the same color you've just seen and try to be as close to that color you just have been shown. And there are, I guess, 5 rounds, and at the very end, you're getting a score how good you are. So I'm inviting everyone to join. Takes you a few minutes, and you can see how precise you are at the very end. And of course, if there are questions or something doesn't work, feel free to ask as well in the chat as well as in the audience.
Okay, I just showed this one as a trial, and now I don't want to spoil it for the others. Try for yourself and see how you're doing.
So Achim is just in the last round. I guess most of you have already played. Can you raise your hand if you need a little bit more time so we know? Okay, we'll give you another 1 or 2 minutes. The experts are dropping down to rank number 21. Well done. So again, I guess everyone finished so far in the room here in the audience. I hope as well at home. As you can see, it's not that easy, and you can see the leaderboard at the very end, and even my expert here on my right-hand side couldn't beat you. This is really not an easy task, and this little experiment shows you how difficult it is to remember an exact color in its colorfulness, in its use, or in its color, tone of color, and also in its brightness or lightness, depending on the color you've shown. Feel free to go through, feel free to play at home with your friends, your family. It's a pretty cool tool for a little game in the evening. Perfect. But with that short interactive interaction with you. Thanks for participating. We would like to continue with our talk. And luckily, typically, as a scientist or as a person in general, we do not often have to match exact colors. So this is typically not the task at hand, the task you just did. But instead, if you're talking about colors and effective color maps, this is the content of our lecture today, we are more interested in combinations, or to be precise, in color palettes. So colors relative to each other make a lot more sense to us when reading or communicating or transporting information than like it must be exactly this blue. With that, I guess Achim will continue for the next few minutes.
Yeah, thanks. And my kudos to the person who scored 47 or something. So I played this a couple of times, and in front of my computer in my office with enough time, and I think 45 was the best I scored. I did it 4 times or something like that. So 47 is really good. And yeah, as Reto already said, understanding that this color should mean this or matching individual colors is typically not the task at hand, but rather we think about colors mapping a certain scale, so a qualitative or quantitative scale to colors, and then using this in some sort of data visualization. And we also call the result palettes of colors. And the classical distinction is that there are three most important kinds of color maps. The first one is qualitative, where the color is used to distinguish different categories. If we would have student data, let's say from bachelor, master, and PhD level, this would be a typical categorical variable. If we think about the climate context, we might have different climate projections from different physical models from different providers and so on. And then we might distinguish these with different categories. Then we have sequential colors that map numeric values, or at least ordered values, that go from high to low or the other way around. And then finally, we have diverging colors where we have a neutral value in the middle. Often this is 0, and then we can diverge to a positive and a negative side of the color palette. But the neutral value might also be something else, 50%, and then more or less than 50%, and so on. Yeah, or again, in the climate context, warming versus cooling, greening versus browning, and so on. And I've used three examples for these types of palettes on the slide, and below the actual color palette, I put a desaturated version of it to show you what is the main idea for making the color palette work. In the sequential, let's start with the sequential one. That's easiest. We should have monotonic ordering from light to dark or dark to light. We'll talk about this with a few examples in a moment, but to have something monotonic when the colors go from light to dark. The reason for this is that light to dark is something that everybody can see. So if you can see, then you can see light-dark contrasts. Whereas differences between different color tones might be more challenging, might depend more on the context and the viewer, and so on. But light-dark contrasts are relatively easy to work with. So this is the main ingredient for the sequential palette. And for the diverging palette, you then use typically two sequential ones. You use the same neutral value, often light gray or almost white in the middle, sometimes also a yellowish, light yellowish color in the middle, and then you diverge to two dark colors in the tails. And you can do it in such a way that when you desaturate the colors, that you are exactly balanced, so that the dark colors at the two ends of the color scale are balanced and not one is more prominent than the other. We will see more details about this in a moment. And in a qualitative palette, where the different categories, the different groups that are coded by the colors should typically receive a similar perceptual weight. There shouldn't be a bias towards one bright, shiny color and the other very light color somehow disappears in the background. They should have a similar visual weight. And we can do this by exactly giving them the same gray value. Sometimes we allow for small uh, deviations in the amount of gray so that the colors are a bit easier to distinguish, but we should make sure that we don't make the brightness contrasts too large, because this is typically associated with large and small. Okay, so that's the basic idea how we can set up color palettes that work, and we will see some more details about this in the following. How to construct exact palettes. But before I go there, let me show you a concrete example. It's not really a climate example per se, but also using atmospheric data. And a few of you might remember this incident. It's been some years under the first term of Trump as president, where there was a hurricane forecast, Hurricane Dorian, and this was projected to hit Florida, and there was a big warning and everything. And Trump claimed that also Alabama was at risk. We will see in a moment more closely on the map where Alabama is. And Alabama was not really at risk. And there was this image on the left where Trump in the White House then drew an extended warning cone with a Sharpie. And this is why on social media this became known as Sharpie Gate, where he just claimed that something else was the truth than the actual thing. But later on, a day later or so, he found, or one of his team, they found a graphic where they said, okay, we can use this graphic to underpin his claim Alabama was going to be hit. So let's have a look at this map that Trump used, especially on social media, to say Alabama was going to be hit. So this is a standard NOAA forecast product, the probability of wind speeds greater than 63 kilometers per hour, and the probabilities at the bottom are shown by a color scale, starting with this dark green from 5 to 10% up to 90 to 100% with this dark purple here. Yeah, so we have this dark purple here in the middle where there's a very high probability, beyond 90%, that there will be a tropical storm. And this is hitting Florida, but then we have other southern states up here, and this region up here is Alabama. And as you see, we have quite a bit of color going through Alabama. And so if you don't look at the annotation down here very closely, then you might still have the impression, wow, there's a lot of color. There is an actual warning for Alabama, but it means that the probability for Alabama was 5 to 10 or 10 to 20%. So it was much more likely that the storm was not going to hit Alabama. There was a low probability, but not very high. But I would argue that the color map used by NOAA for this product is not ideal. One reason are these very flashy colors. Yeah, that's even here in the margins for 5 to 10, 10 to 20, and 20 to 30%. We have really bright and flashy colors. And these draw attention to a plot, if we want it or not. This is what our visual system is built for, or is good at. The next problem is if we emulate a certain red-green color vision deficiency. That means that certain differences that are clear to someone with full color vision are not clear to someone with this certain kind of red-green color blindness. So I'm simulating something called deuteranopia here. So maybe there is someone in the audience or online who can confirm this. So for a person with deuteranopia, this color map and this color map should look similar. Maybe not exactly identical, but similar. And then you can already see that for a person with this kind of color vision deficiency, it becomes very hard to say what is what, because we have these middle yellowish colors and then these brownish colors on both sides. And yeah, if we make assumptions, we might be able to say, okay, these will be low probabilities, these medium probabilities, and these high probabilities, but we have to make assumptions for that. It's impossible just by looking at the map to decode this. And typically, color vision deficient viewers are quite good at navigating around these things, making the right assumptions to still operate. But clearly, we don't make it easy for them if we use a color map like this. And the same we see when we convert to grayscale. Yeah, we see that we have this change going from dark colors for very low probabilities to very light colors for medium probabilities, and then going to dark colors again. And this non-monotonicity in the color scale makes no sense. Yeah, we should go from light to dark. Light is something that goes more in the background, and dark stands out more because the darker colors can also be more colorful. And so this is a color map that I would propose to use as an alternative. So we start out from a green color in the tails here, and then we go to the purple color, but we do it in such a way that we go from light to dark. And this immediately gives much more visual weight to the area with the highest probability, whereas the areas with the low probability move more into the background. Yeah, and we don't create artificial distractions by having this very flashy color scale with no intuitive ordering. So let's see how this image is doing when we coerce it to grayscale, and then we see it still works. So even if we remove the color altogether, just in grayscale, it's still okay. We can see some more fine details. It gets a little bit easier to match a certain band in the plot to a certain interval in the legend at the bottom. But for getting the main picture across, it still works. And also, if we collapse the red-green contrasts, again, emulate deuteranopia, it still works. Yeah. And we don't have a disadvantage for the colorblind viewers. And so the changes you need to make when constructing the palette are not that huge. You can still go from green to purple if you wish to do so, but you need to know how to do it in such a way that you can go from light to dark and from not very colorful to more colorful. And this is what I will show you next, how you can do this yourself. Yeah, so we need strategies to construct color palettes, color maps with better perceptual properties, and we then need tools to assess these color maps, so we can emulate color vision deficiencies easily, for example, but it also helps to separate the perceptual dimensions. What is the color hue, the type? Is it red, green, blue? What is the brightness? Is it very light? Is it very dark? And how colorful is it? Yeah, so work with these perceptual dimensions and manipulate these more easily. And typical color picker tools, so if you open Photoshop or similar utilities, they have color pickers, and also by now the color pickers are better than they used to be, but in many situations I still find it relatively hard to use the color pickers to pick a color map that has nice perceptual properties. So yeah, if we don't want to end up this, because clearly Bob Ross wouldn't approve, let's see what we can do to do better. And we will use a tool, a certain so-called color space that works better for picking colors that match the human visual perceptions than the RGB colors, red, green, blue colors that we are used to. Yeah, so here on the right, we have these RGB colors. We have a red, green, and blue channel. And this is how colors used to be generated on CRT displays back in the last millennium. Modern displays don't generate colors with 3 color guns emitting red, green, and blue light, but they still use the same tools to describe the colors. They use triplets, mixtures of red, green, and blue to describe a certain color. And that might work for a display, but it does not work well for a human. Yeah, so instead, there are other color models, so-called color spaces, that better capture the dimensions of the human visual system. And the model I'm using here is called HCL for hue, chroma, and luminance. Hue is the type of color. What we varied in the example for the qualitative palette, here going from red over yellowish, brownish to green, blue, and purple. Then we can vary the chroma, the colorfulness, going from gray to something very colorful. And then we can vary the luminance going from light to dark. And maybe to emphasize this, especially in the second row here for the chroma, if you would print this out on a grayscale printer, all areas here would have almost the same gray. So they really just vary in the amount of color, and they all have the same hue. So they are all red, but because they are not colorful, or because this is not colorful, we don't see the red. Then we have this a little bit reddish gray, and then it becomes more and more reddish. It's always the same hue, but a different amount of colorfulness. And also here, we always have the same hue. It's a certain blue I've picked here. I've not made it very colorful. I picked a low chroma value, and then I go from light to dark. Okay, and with these tools available, it is possible to really just vary one dimension, just vary the hue, and keep, for example, chroma and luminance fixed. And this is here in the middle. I have a rainbow palette going from red over yellow, green, blue, purple, back to red. So once round the color wheel. And at the bottom, I have the corresponding HCL, hue, chroma, luminance coordinates. And we see hue changes from 0 to 360 degrees once around the color wheel, whereas luminance and chroma have been kept almost constant at a certain value. So I have moderately dark colors and quite colorful colors for this display. And at the top here, I have the corresponding development of the RGB coordinates. So red decreases, then is almost zero, and then increases again. And green goes up and goes down, and blue goes down and up. And you see, these coordinates go all over the place. And it would be very hard to pick these trajectories in red, green, and blue to generate something that has constant chroma and constant luminance and only varies the hue. Yeah, so we need this computational tool letting us move in these HCl coordinates. Then we do it the other way around. We pick a rainbow color scale as you all have seen it in some visualization somewhere. This rainbow color scale used to be extremely popular until I would say 15, 20 years ago. It was really almost everywhere in a lot of science publications. Things got a lot better since then because there were numerous publications, including our own, um, pointing out that this is a bad color scale, but you still see it in quite a few places or variations of it. So here we just go once around the RGB space from red, yellow, green, blue, purple, back to red. And you see that we have these really regular trajectories going up with green and then going down with green, going down with red, going up with red, and so on. So we have very simple trajectories in the red RGB space. But if we look at the perceptual properties in this HCl description, we see, well, the hue doesn't change linearly, but we rather have a certain step function. We really prominently have green, blue, and red in the palette, whereas yellow and purple have much smaller intervals. Also, the luminance is first darker, then goes to light colors. The yellow is much lighter, the green is also very light, then it goes down again and a bit up again. So I have this change in luminance that I cannot control easily. And the colorfulness, the last line, is also all over the place. Yeah? So picking colors, a good set of colors, a palette that cooperates, where the colors cooperate with each other, is really hard in this color model and much easier in HCl. There are some other similar color spaces. HCl is not the only one, but it's one that is very easy to use and we propagate here. Okay, so let's come back to our palette construction then. We wanted to do sequential, diverging, and qualitative palettes, and I've picked 3 sequential palettes. All of them are variations of blue palettes, and I'm showing you the trajectories I used for that in this HCl space. So for the first, for this blues 2 palette, I used a constant hue. So all of them are exactly the same kind of blue. And then on the left, I have a dark color and I go up to a light color with a slight kink in the curve. And similarly, I go from very colorful to not so colorful. And I don't go up to a full white, I end at a grayish color. This is easy to see the ordering, but the colors are all a bit mute. We don't have anything really bright, and we can change this if we want some brighter colors. We can make the chroma trajectory triangle shaped, so that we still keep the hue, the red line, almost fixed, all the same blue. We still go from a dark to a rather light color, now a bit lighter than before. And we go from quite colorful to a bit more colorful and then down to not colorful at all. And by using this triangle shape, we get a little bit more of differentiation in the middle of the palette. We still go from dark to light. We're still monotonic in luminance or in brightness. But in the middle of the palette, by going up and down with a chroma, we have this effect that these colors are a bit easier to distinguish than they were in this way. So here it was smoother, which might be what I want. But if I want to have more discrimination along the entire scale, then this works a little bit better. And I can increase this effect a little bit more if I change the blue. I go from a certain blue hue to a different blue hue. So the curve goes a little bit down. And this further increases the discrimination along the scale while keeping the luminance. So
Okay, perfect. So sorry for that technical difficulty. And back we are. Thank you very much. So maybe I repeat one or two sentences for those who have not heard what I've just said before. So what we can see here on screen now is the spatial plot for the relative change of precipitation based on the ensemble of the coupled model intercomparison project version 6. So basically it's a climate projection and the expected relative change of precipitation. And as we know, with a changing climate, we're expecting areas where it gets drier. We're expecting areas where it gets wetter. And if you think about that, we now switch to a different type of color map. So we have a neutral point again. If nothing changes, this is the least important for us maybe on this plot, but we can now have areas where it's getting drier, or on the other extreme, it can get wetter. And this is a classical example where a diverging color map makes a lot of sense. So we have been picking, again, one of our default palettes. This is called the red-blue color palette. So you can see that in the center, we have little chroma, so it's close to gray. And then towards the both extremes, so going away from zero, we both increase simultaneously on both sides, not only the luminance, we decrease the luminance, sorry, to get to darker colors, and we increase the chroma to get to more vivid, more flashy colors. And the only difference between the positive side and the negative side is that we have a constant U in the red area on the positive side, and sorry, on the negative side, getting drier, and a blue U on the positive end. But they're completely balanced, again, on the principles Achim explained before. So we're not highlighting one extreme more than the other. They're only differentiated by its U. We have seen a series of different maps. I'm just selecting the same color maps as Achim has just shown the slide before. So if you're not a fan of reds and blues, what about greens and browns? Based on the same principles, works the very same. We have simply changed the U, not the information provided, and also can highlight here easily that like brownish means drier if you think about vegetation, while green, more precipitation, maybe means a greening. So it depends a little bit on the context you are plotting these graphics for. You can choose different U's on your personal preference or the context, but the principles behind these color maps is the same as shown before, and again, should work for everyone in the audience or whoever sees the graph. Switching to a different type. So rather than having a spatial plot, we now have a temporal plot. And I guess most of you sitting in this audience or online know this graph from somewhere. It's the projection of the IPCC. So this is the original colors and the original data as shown in the IPCC AR6, so the 6th assessment report for 5 different scenarios, and they're of the temperature projection, up to 2100. And if you look at this plot, it looks actually pretty nice, right? Looks okay. We can see on the right-hand side, we have a legend. The legend actually shows the light blue first. That's SSP scenario 1 with a roughly 1.9 degree warming expected. SSP1 with a different flavor with 2.6 degrees. SSP2 with 4.5 degrees. This is what we've shown on the spatial plots. And then SSP3 and 5 with even higher expected average temperatures on our globe. Can you spot anything which could be improved on this graphic if you look at it? Yes, maybe? Exactly, this is exactly one of the drawbacks. I repeat it for the audience online. So one of the participants here highlighted one of the issues. What we could do is to switch the two blues on the lower end. Why? Currently, if you look at it on the legend, it's easy to see. The top one is the least extreme, going to more and more extreme warmings. But the first line is actually a light blue, then a dark blue, and then jumping back to a light orange. So the order there makes no sense if you think about it, as just heard before, the lightness. So maybe just switching the light blue with the dark blue would already help us. There's one other drawback on this figure, which makes it a bit more hard to read. Maybe I solved that mystery myself. Compare the order of the lines in the legend with the order of the lines in the plot. They are exactly inverted, right? So your head must now flip everything. Here in the plot, the most extreme are on top. In the legend, the most extreme are at the bottom. So we can easily fix that by inverting the legend, or we can make our life even easier because we have enough space. What if we do this? Much easier to read. We haven't switched the blues, kept the originals, but if you look at that, it's way, way easier to interpret the information shown here. This is called direct labeling. So we're directly labeling the different scenarios, the different trajectories here in the plot. The colors, we heard there is one flaw in here, but it's actually not too shabby, not too bad, but we decided to switch that to some of our suggested palettes. So what I do on the next two slides is simply replacing the 5 colors here. And the first variation here is also a categorical palette from the package. This is the Okabuito palette, where all 5 colors are relatively balanced. And now we have also switched the blues on the bottom, which makes it already a little bit easier to read and quite nice colors to look at. Thank you. And they can be discriminated by everyone. So even people with a color vision deficiency should be easily able to differentiate. Although you don't really have to do it here because we have the direct labeling helping you with that as well in this specific plot. We can now, of course, change that. So we did the following and applied a diverging color map on here. It's again a version of the red-blue. So we say SSP2 in the middle, that's the intermediate scenario. That's basically the projection we are currently on somewhat. And with using a diverging color scheme, we can now highlight both extremes. So if you look at this graphic, the least, the information which jumps least into your face, let's say like this, is the one in the middle, which is the intermediate scenario. But with the darker and more flashy colors towards the extremes, you can relatively easily see where the two extremes are. So if you want to more transport the extreme edges or the extreme ends of the scenarios, that might be an idea. But maybe it's not about the extremes on the low and the high end. Maybe you want to warn and just highlight the warm extreme. Well, what if we switch to a sequential color scheme here with 2 different hues going from a light, relatively light yellow to a very dark violet, relatively speaking, and that now highlights the upper end, so the scenarios where we can expect up to 8.5 degrees of global temperature increase. So as you can see here, first of all, there's a variety of effective color palettes you can choose from, but it also depends on what you want to transport. Or in other words, depending on what colors you choose, you are transporting different information. This is a series of qualitative palettes, I guess just an addition to the set we have shown before. So if you go back to this and want to use qualitative palettes, there's a series of different palettes and different software as well. Again, they are designed in a way that most people can differentiate between the colors, or they have other very nice properties. How can you make use of it? Well, some of you are programmers, I know, seen them. If you are programming in Python or R, 2 of the common open source software used in science, in I guess most fields, we have written packages for that. So in R as well as in Python, there exists a package called colorspace. All our graphics are based on these 2 packages. So feel free to download and use it. There's also documentation for both packages online where you can find a lot of information. But maybe you're not a programmer yourself, right? But we want to maybe use or check the colors. And we also have tools for that. And the website for that is called the HCL Wizard. HCL again is hue, chroma, luminance, the concept introduced by Achim, and you are the wizard in this in this scenario. And on there we have a series of tools which you can interactively play with. Let's have a quick look at it. And jump onto the hclwizard.org website. If you're interested, we do have a lot of interesting examples here, and also Bob Ross's little happy accident, and a few other great examples on how not to choose or how to choose colors. But maybe most important are the three apps up here. We do have a palette creator. So if you click on that, and the computer actually loads the page, you can see an app which is also available in a Python and R implementation if you don't want to use the browser version. And this is exactly a tool to create the palettes shown by Achim, for example. So you can see in the middle section, you can specify hues, chromas, and luminance. For example, if I don't like that palette, I can simply say, I want to have a different hue on one end. So I moved the bluish colors into greenish colors. Or I can say, well, the white is too white. I want to have a little bit a darker end, so a bit more gray on the right-hand side of the palette, and then also play around with that. So if everyone tries it at the same time, maybe my server dies at some point, but let's let's try it out. So just for you, if you want to play around on the left side in the navigation, you can also find all the default palettes. For example, if we say our basic sequential multi-hue, you can see a lot of presets. If you click on one of these presets, the sliders will be adjusting to our predefined palettes, and then you can adjust them to your needs if you want to change something or have a look at it. You can also change the type of plot. So for example, before we had line plots, you can also use a different demo and say, okay, how does that work on line plots, spine plots, and a lot of different data sets at hand. But how can you use it? Well, let's say I would like to have this wonderful color palette I just have here. I need maybe 4 different colors. You can simply go onto the export tab, and here you can see different information. So on the left, the matrix here shows the HCL coordinates, maybe not too important for you. We have the RGB coordinates in the middle, and we also have the hex colors. And for those using colors, I guess the hex colors are the most common ones. You can simply download that or use them wherever you need to. Yes, thank you. I can show that here as well. So let's assume we go back to the infamous RGB color map. This is just here for legacy and for demonstration. This is now, of course, not the best color map, but what you also have included here in the tool, you can, of course, also do it with the nicer palettes on the left-hand side. You can say, I would like to emulate color vision deficiencies. So on the left hand, I'm clicking on Deutan. This is the deuteranope vision. So this is the common red-green color blindness. And you can immediately see how a person having this deficiency will perceive the color scale you've just chosen. Of course, if you do that with more balanced and more effective color maps, they should all work pretty nice. So this is the red-green color representation for people with red-green color blindness. This would be for protanope or tritanope color vision deficiencies, which are relatively rare, but you can also emulate how they may perceive your color map. But that's not all. Maybe I'll show the second tool, which is also pretty fun and maybe useful for yourself. This is the deficiency emulator. And here, with this tool, we don't provide you the functionality to design a color map and then test it, but rather, let's imagine you have a figure, your colleague has a figure, you'll find a figure somewhere, and you want to test it. How does a person with a restricted kind of color vision see or perceive things? Do we have an example image somewhere? Saving this. Unbenannt.png, of course, the best name ever. So let's imagine we have this, can be a screenshot, can be a figure you find somewhere. What you can do here is to emulate color vision deficiency. You can also adjust the strength, how strong the deficiency is. Let's say someone is fully red-green colorblind or has an extreme deficiency. We can now simply say, please browse the files. Go to image, upload, it accepts PNGs, JPEGs for up to a megabyte, I guess, of size. And then the system or the server calculates the deficiencies. So on top, you can see, first of all, the original, but what is the perception of a person with red-green blindness? Sorry, this is the desaturated version, the grayscale version. And this is how the map looks like for a person with red-green blindness. Does it still work? Can you still read the information? That is the question here, and an easy test if you want to test a certain figure or graphic. Of course, we also have the same for Piotranope or Tritanope. Again, they are relatively rare, but you can test and also support people with these restrictions. Or you can have a look at all of them to figure out if it still works or what possible drawbacks or advantages of color maps are. What time is it? Okay, so maybe I don't show too much, but there's a third tool here. You can play around with it yourself. It's the color picker. This is also based on the same HCL space, and this allows you to pick specific colors. The big advantage here is that you're not moving around in the RGB space, where we have learned that it's very hard to specify specific colors, but we are again in the HCL space. So just for a quick demonstration, let's say I'm interested in getting a series of reds. What you can see here is a slice through that HCL color space, which is a three-dimensional space. And I can say, okay, I would like to have this very saturated red here, and simply pick it. And the advantage is now that in this HCL coordinates, I can say, I would like to have the same red with the same lightness, but I would like to use reduce the chroma. So it should be, the next color should be a little bit less colorful. I can say that's perfect. Pick this one, maybe define a third one, pick this one, and just for demonstration, last one, and pick this one. And below you can now see the colors I've picked. Again, with these very nice properties that they are all the same hue, they are all the same luminance. All we've changed here is just the brightness, the chroma, sorry. Feel free to play around. There is also a different slice through the color space in a different way, where you can see what happens if you change the hue, but not the luminance and chroma, and which colors are defined to pick effective maps or colors if you just need a couple, while if you need actual color maps, then the color palette creator might be the tool of choice for selecting specific colors. So links are all in the slides. Feel free to try it out. And with that, I would like to hand back to Achim with a short wrap up and some recommendations before we then jump into the last part of our lecture.
Yes, thanks. Okay, so for the wrap up, so while we talked a lot about color, mostly in the presentation. My first advice would be, okay, is color the best way to convey information in your setting? Or can you do something different? So if you have the possibility, so if the point is mostly about getting the information across, getting across what is in the underlying data, if you have the option to use something else, to use something along a certain axis, like a line plot, a scatter plot, and something like that, a bar plot, as we showed before in the warming stripes. So a plot like this is easier and quicker to decode for humans because we have the y-axis that lets us discriminate the different years, and the color just adds to it. I would argue, but there are also situations where color is really quite useful, like in the world map that we showed you, where if you want to combine the geographical information with another dimension, then this kind of display works, but it is important to use an appropriate type of palette for that. Yeah, the good thing is you don't need to reinvent the wheel. By now, most software packages have quite good palettes available. They typically also still provide the not so good or even ugly or actively distracting palettes like the classical rainbow, but usually it doesn't take much effort to get something better. Um, the if you're coloring areas like in the world map example or in the Dorian example, I would recommend to use high chroma, um, colorful colors, um, a bit more sparingly, because otherwise it can be a bit much to take in. Um, and so in general, if you shade areas, a little bit of color is often already enough. If you're coloring smaller points or lines, then a bit more color is often useful because you have a lot of white background anyway. Well, if you do have a light background, if you use graphics with a dark background, then the colors that would stand out will be lighter, and but still with a lot of chroma. And yeah, if you do something, especially if it's intended for a wide audience, it might be different if you do something for yourself and your collaborators, your advisors. Then maybe you don't have to care that much about the palette being robust, because you know the setting and you know the viewers looking at it. But for a conference presentation, a paper, or even something that goes out to the general public, robustness is really important, and check it. Yeah, and if you can do some tricks like the direct labels on the time series graphs, do that. Yeah, if you can do something that helps those who cannot see the colors, go for it. Um, then at the end of the slides, we have some credits. The data sources we have been using here with the corresponding links where we got the data, the colors, and so on. And at the very end of the presentation, I have some references. The first two references are our software papers introducing the Python color space package and the R color space package. And at the bottom, there's another publication about using colors in meteorological visualizations, which is not exactly climate, but I think there will be some useful examples in there if you're interested in that. So we should still have a little bit of time, like 15 minutes or so. Yeah. So to let you try to use this in practice, we have made some color assessment, put some color assessment tasks together for you. I will show you in a second where you find them. They are next to the presentation slides in the OLED course, but I will briefly go through them. So we picked some publications on climate topics, a classical Nature paper about changing temperatures, and I picked out two graphics from that, changing temperature around the world, and then specifically highlighting California here. There was the one that Reto used before, then the velocity of temperature change by biome from the same paper, a graphic about productivity loss in Brazil in high intensity work in different projections, and finally a severe weather warning map by UWZ. For Austria, this was the week before Easter. You might remember that we were almost ready for spring, and then winter came back with force. And this is one of these days where the severe weather warning in this map mostly pertain to a warning because of snow. And I would encourage you, talk to your neighbors, especially, I mean, if you're sitting together, that's great, you can discuss already. Those who sit with few more spaces, talk to your neighbors, look up the graphics and discuss a little bit. As a starting point, you can try to upload the graphics into the HCL wizard to emulate the color vision deficiencies. Maybe you also spot some other problems that things that you feel should be improved now that you've heard this presentation. For those online, we will create some breakout sessions, discuss with each other, and post your feedback in the chat. So we will give you some 10 or 15 minutes, maybe 10 minutes, and then we have some 5 minutes to wrap up together. I will just quickly go to the OLED course. If you go to the OLED course and the presentation slides, then we have here 2 files with the tasks. You can either download the HTML or the PDF version and then look at the graphics, discuss a little bit, and please give us feedback through the chat, and then we will do some wrap up in about 10 minutes or so. Thanks. So if anyone still wants to post a couple of comments for the graphics from the tasks, feel free to do so. Reto is just uploading some of the graphics into the HCL wizard. Okay. Okay. So time management was suboptimal. So we don't have time to go in detail through all the graphics. So let me just quickly provide a couple of comments, and I will also look at the chat afterwards and maybe write back if you're still writing something now. So the first graphic with a classical rainbow, I think we've brought the point across before that this is a bad choice for a number of reasons, and this is the reason why I also had to pick a paper from 2009, because in 2026 you rarely find pictures like that in nature, especially in climate. This one is more challenging. So here we want with the biomes, we have, I think it was 14 different biomes being distinguished by color, and then looking at these velocity distributions. And I think that the velocity distributions at the bottom work quite all right, but matching these distributions to the world map above, this is really challenging. And I don't have a really good answer to what we should do, but I find it very hard to look at this map, and I would need to play around with this some more.
Exactly. And if you look at this example, this is what you did with you in the very beginning, right? Matching exact colors, and now over like some distance, looking at the bottom and then going up and then say, oh, what is this yellow or that yellow? And for those interested, there are also some scientific papers where they did an experiment. If I offer you 5 different colors, the success rate of mapping them is about 85% or higher. If it's 7 or 9, up to 9 colors, it drops to 20%. So having so much distinct different colors is a very, very difficult task and not the best choice, just as an add-on on what Achim just said.
Yes. So in a printed paper or in a PDF, in a static file, this is challenging no matter what you do. In an interactive context, it might work better. Yeah, this is also a rainbow palette. I won't say too much about it. I think it's even worse than the one from the older paper for a number of reasons. But let me finish with this last warning map, having 1 minute left on the clock. So this is the one where Reto just also generated um, the color vision deficiency versions of it. And then you can see, so this map and the map I showed you before will look more or less alike for a person with a certain red-green color blindness. Or with this other flavor of red-green color blindness, you would get this. This is still reasonably common. And then you see it doesn't really work very well for these categories. Maybe the two upper ones still work okay-ish, but they're clearly not great. And in this way, even worse. And so I really wonder if I have a warning map that is designed for the general public, why I would do something like that. It's really would be very important to pick colors that work better, that are more robust for a larger audience, and yeah, doing a similar trick as for the Dorian hurricane warning would work quite well here and would not be very hard to adopt.
Exactly. And for most of us, this is kind of, well, it looks good, right? Green for us is no danger, red is a lot of danger. But as we heard in the beginning, about 8% of the male population in Europe have some sort of color deficiency, i.e., if this is for the public, you miss 4% of your inhabitants. They can't get your warnings. They're either, I say, dying, they're even in severe troubles, or everything is fine. They just can't read that graphic. And just as a last sentence, maybe before or when planning this lecture, we also got the input, well, but sometimes there's a preset colors. We need to use exactly these colors for, I don't know what agency. Yes, but we think it's not the most important aspect to have the exact color. It's way, way more important that they work. And just saying, well, it was always done like this, is a bad choice of colors. So think about it. And also when you go to seminars in the future, have a look at the colors presented. If you see it once, you will always see it, and you can improve your own life and your own graphics and also spot potential issues and problems. I guess from my side, thanks for listening. Thanks for being around. Have a colorful day, and giving back to Achim.
Yeah. Thanks, everyone. Thank you.
Yeah, thank you, Achim. Thank you, Reto. And for you, just remember your task. You have a special task in the task description, which is just about this stuff. We have some example, and you can work with the tools you've learned today. So hope you learned something today and have much fun with the task. Thank you, and see you next time.